out in some paper. Ising game is a Drosophila of in between physics and say game theory and optimization and stuff. And so what I will tell you about is this binary, what is called in game theory, a binary choice noisy graphical. Games, this is a game played by an agents placed at the vertices of a graph characterized by some adjacency matrix, and the agents are equipped with a set of strategies, which in this case are just two strategies, choosing say 1 or -1, and the utility of each agent, which in game theory is something that determines what the agents do, contains an additive random contribution which makes this game stochastic, and a usual assumption is that this contribution is known to the agent but unknown to his or her neighbors. And
sorry.
Yeah?
It means that each agent, this is what you call payoff usually.
Yeah. Well, you don't need payoff here. You just the agent makes his or her decision based on the utility of this decision. That's sufficient here. So, and so there is a distribution. Of course, you have to assume something on this stochastic contribution, and I will tell you about two very recent results, and these two papers will be out very shortly. The first is on myopic Ising game, where we were able to identify the game theoretic nature of this equilibrium, and another result is on the strategically thinking agents. This is a paper with Georgy Broninsky and Yekaterina Serebryannikov, who is present here. This is a result on something that we call stochastic cooling. So let me first describe the choice. So the utilities of all agents contain stochastic components, and as I told you, these stochastic components, the realization of them is assumed to be known to the agents, but you don't know what are the realizations of these variables for the neighbors. And therefore, the decision cannot be exact. It should be based on the expectations of an agent concerning his neighbors. And these are these expectations. Otherwise, you see a typical Ising-like expression, which is linear in the expectation and linear in the strategy. And so the strategy SI is prefers to minus SI if the corresponding expected utility is bigger. And then you can easily calculate the probability of taking this strategy. This is just a regular distribution function, which is a trivial result. And in particular, you can compute the probability of choosing, say, +1 here. And now, if you translate it to the game theory language, then this randomness in local utilities is equivalent to a mixed strategies type description. When you tell mixed strategies, you in fact assume this is a very strict assumption. This mixed strategies means that these stochastic components are independent. This is not a realistic feature, but this is somehow typical for game theory. Game theory needs some evolution to become something realistic. And there is a special equilibrium which is called Quantal response equilibrium, introduced in I guess in 86 for the first time. And this Quantal response equilibrium is a set of probabilities of mixed strategies, means that you describe probabilities for decisions. And then Quantal response equilibrium tells you that these probabilities are self-consistent. So the your expectations with respect to your neighbors are consistent with the neighbor's expectation on what your decision will be. And this gives you a set of equations for these probabilities written here. Because of course now you see, instead of the expected mean strategy, you have these QRE probabilities here. And of course you can easily rewrite this in terms of the equilibrium averages. And these are equations that are already very similar to what you might have seen in the literature on statistical physics on graphs, for example. With a very important caveat that in statistical physics, the only kind of matrices that, the adjacency matrices that you can study are symmetric. So this graph cannot be directed, because energy is a property of a link, not of a node. And game theory is broader in this sense, because utility is a property of a node and not of a link. So this, but this is not, I'll probably comment on this a bit later. So these are equations that just manifest what QRE tells you. And then if you take a complete graph, you get a well-known result of Brock and Durlov from 2001. So here we just, they were not able to identify the game theoretic nature of the equilibrium. It was described, but they just wrote that this is some kind of Nash equilibrium without being specific. So this is the first thing that is new here. Now, just to orient you, if you make a strange choice and choose a Gumbel distribution for the stochastic component, you get what in physics is called Curie-Weiss equation. This is an equation describing phase transitions in magnetics that was obtained in, I don't know, 1920. And then if the external field is 0, you get standard phase transitions. And you can just see where these transitions happen, which is this conditions, which is this condition here. Now, an interesting thing here is that one of the biggest problems in game theory is that if you have static equilibria, you don't know which one to choose, because you have no somehow gauge on it. And the only case in which you do have this gauge are so-called potential games, where you have something like an energy in physics. Only within this special class of potential games, which can be formulated only for undirected graphs. Only in this case, you can have something similar to energy, and then there is a theorem that the proper equilibrium is the one giving the highest, the biggest potential value of potential. Now, in this case, it's interesting that at least the result for the complete graph is in fact a solution of the optimization problem, which is a minimum of the so-called free energy, or what in physics is called free energy. There is no game theoretic formulation for this, because we don't know how to what is the potential for the game in which utilities have stochastic components, but still the result that you get, at least for the Gumbel distribution, is equivalent to an optimization problem. Now, there are very few cases in which competitive equilibrium is equivalent to the solution of the optimization of any optimization problem. This is one of these cases. And something that relates what I'm talking about to what Stefano was just telling, you can use a very useful approximation called an annealed approximation, which basically tells you that you use something like a configuration model to replace the adjacency matrix by the adjacency metric of an effective weighted graph, so that Gij's are the probabilities of forming a link in the configuration model, and then you can write an explicit. You can write explicit equations for the local averages, and this is what was told. You see, the threshold of the phase transition does heavily depend on fluctuations, and there are cases, say, when this is infinite, then the threshold is at infinity, and this is what is so important for epidemics, when they suddenly found out that the epidemic threshold can be absent. Now, I'll briefly tell you what we did on dynamics. In general, such system is described by the multivariate distribution. This is a general description that in principle contains all correlations, which in game theory would correspond to studying correlated equilibria, which is something that has still to be done. And so this conventional independent choice tells you that you assume that this is factorized. And the temporal evolution is just given by flips. And you can write a standard master equation assuming Poissonian nature of the events. Now, in principle, what you do here, you replace this strategic thinking, or just thinking about static equilibria by something that is either myopic or myopic plus memory, or importantly, myopic plus strategic thinking, which is very special to game theory and artificial intelligence also. There's a voluminous literature on what happens to multi-agent systems depending on which component you take into account and with which weight. Now, this is a standard evolution if you assume that you can have only one flip per infinitesimal time slice. And then you have to choose this flip probabilities. That's the thing you can tell. And you see that here you don't have expectations. You have the decision in this myopic case is based on the configuration that an agent sees immediately, so to say. So just he has a chance of choosing something. He looks around, and based on what he sees, he calculates his decision. And then you can you can show that in the mean field approximation you get the same answers as we get in as we got in the static case, which means that there is something very interesting here, namely mean field approximation is of course not exact, and so there is something beyond mean field here, which is interesting. Now this was somehow expected because it's not guaranteed, say, that best response leads to Nash equilibrium dynamically. But anyway, the space is somehow much better mapped than before, and this is just a comment. In principle, you can take into account correlations, and then what you study is the so-called correlated equilibrium, which is considered by many experts as the most fundamental thing in game theory. And now the second result is on adding strategic thinking, and I'll be brief here. Just walk you a bit through this slide. This is done for the complete graph, and so the only thing that is important is the number of agents taking +1 or -1 for here, and so this is denoted by n plus and minus. The instantaneous utility is the same as written before, and if the agents are thinking strategically, then they base their solution not only by the instantaneous scene in which they find themselves, but also on their prognosis of what will happen to the system. And a typical way of handling it is the expectation which is discounted, a discounted expectation of the trajectories expected by the agents. And there is a technique for solving this, which is called Bellman Equation. You have to write Bellman Equation and solve it. Now, this is the case in which the complete graph game, in which Bellman Equation can be solved exactly, numerically, of course, because analytically it's almost impossible anyway. But for the complete graph, one can solve it exactly, and for a graph with non-trivial topology, you have to do some kind of approximation. Here now, let me skip all the details on the solution, because there are many of them, of course, and just tell you the results of the simulation. Now, what you see here are pictures in which you see the states. The +1 is whatever pink, and -1 is blue, and you compare what happens to the system. Now this is the player's number, and this is time, and you could compare how the system evolves in the myopic case and in the case where future is taken into account heavily. The discounting factor is large. Now, this result can be formulated in a clean and simple way just here. This is a parameterization of what you see, and the result can be formulated as follows. The decision the probabilistic nature of decision is described by this distribution function that just tells you how noise is treated. And so what you see is that if an agent looks far ahead, the effective temperature, the effective noise is much weaker. So you see that thinking beats the noise. I actually have never seen anything like this before. I'm sure somebody should have seen this in some framework. But I didn't see it. Now, after you get this result, it's very clear that this is something that should happen. But it's nice that we can see it very explicitly here. And of course, when the game is almost over, say at step t capital -1, the noise is the default noise. There's no correction to it. So if we skip all details, this is the result which I find very interesting actually on what strategic thinking brings in. Now this has implications for many different problems, because an agent type or multi-agent type representation of optimization problems or problems in artificial intelligence is one of the basic ways of thinking of these systems. And now this is and here this is done in a setting which is familiar to both physicists and game theorists. So one can add additional features here like topology or memory or other effects and study this in detail. In addition, the Bellman time thinking is not unique. One can do more sophisticated. One can think about more sophisticated patterns of strategic behavior. So this is what I have told you, and thank you for your attention.
Questions, comments?
Can you go back from the picture? Yes. So I noticed that the time is from 970 to 2000. Although I would say it's very small diapason, and I guess from the picture that if time becomes smaller, then it becomes more vertical. No, how can you explain this? What happens when t times 500?
It's clear. Again, to this effect, for this effect to show up, you need time.
Yeah.
And so, if time is short, you will see the effect will be small, and actually the steep one is where the noise is almost absent, right? So this is a best response.
And that is in smaller time, right?
Yeah. No. This is no, vice versa.
But then I don't understand the picture, because it says on the right hand side time, and the red means for 970 and the blue for 1000.
It's, you see, if you
970 is 30 units away from 1000, right? And here you have cooling. You are much cooler. If you move to 1000, you have less time, and it flattens.
Ah, it's the other way around.
Yeah. Well, it's you see the step function is the best response.
Yes.
And this is what is called a softmax, or smoothed best response. And so you see, it's the closer are you to the end of the game.
Okay, so
Yeah.
I didn't understand. This was the
So,
Bellman type. Yeah, now.
yeah, but still, just to draw it, it's so. Actually, if you allow me, there is one more comment here. There is an idiotic, somehow, point in game theory. There is a big difference between a game played at the infinite time interval and finite time interval. And this is something a simple physicist cannot understand, because of course, if t is, say, an age of the year.
It's very logical from point of view.
It's in physics there would be no physics as a theory if something like this would be important. For example, quantity, an S matrix which describes scattering. One assumption, that crucial assumption there, is that we assume that interaction dies out very far away from, and without this assumption, physics wouldn't be able to calculate anything. So this is something. This is an artifact, I think. Like many things in game theory, well, it's still a very mathematical subject, not tailored to solving practical problems. This is one of the game theorists agree with this, because, say, mixed equilibria, you first define mixed equilibria because you can use a Brouwer theorem. That's the only reason. And then you get 2 Nobel Prizes explaining how this notion can appear in anything that resembles reality. 2 Nobel Prizes. One of the Nobel laureates, Zelton, changed his opinion on the way, on the subject.
Well, I don't argue that.
Yeah. It's. I'm not against it. You know, each science has its own logic, but now game theory has to become a practical tool, because it's extremely important not only for the economy but for artificial intelligence. Say it's a question number 1, and so here we had to cut the game. Here, this is related to your question. We had to use a version in which players know where it finishes. Now, one of the ways to deal with this is to assume that the game is finite, in fact, but the players do not know that, say, this t is coming randomly.
Yeah.
This is one of the things you can do to improve this. Yeah. Okay.
More questions or comments? Okay, let us thank Andrei. Now we have coffee break.